Let's talk about Newton's method. What are we talking about? Let's say we have this function and we are looking for the root, the position x, where f of x is 0. And what do we have here for this idea? We have some initial starting value, and we know in the vicinity of x0 there is a root. And what can we do? We are looking for the root, or maybe there's more than one root. Then we are looking for the roots of the function f of x. And our idea is the following. We approximate the function by the tangent, and then we find the root of the tangent. And it's clear, more or less clear, that this is not the root of the function, but it's hopefully close to the root, and then we can iterate that process. Now we are here. Let's take the tangent, and the 0 of the tangent in that example is very, very close to the root we are looking for. Okay, so what do we have to do? What is the tangent? It's the equation y is equal to function value f of x0 plus the slope times the deviation from x0, x minus x0. This is a linear function, this is a value, this is a value, this is the variable, this is a value. So if you multiply, it's a linear function. If x0 is the input, then you have a 0 here, then f of x0 is the output. So the line, the straight line, is interpolating that point, and it has the correct, the desired slope. This is the slope, and so this is indeed the tangent. And now we are looking for the root. Don't forget, this is a known, and this is the unknown x. So the root is 0. When is the value 0? For which x is this value 0? So we can write this way. And now let's find the x. Minus f of x0 divided by f prime and plus x0. So this is the root of the tangent, and so we have x1 is this root, so x1 is x0 minus f of x0 divided by f prime of x0. If you remember that formula, but you don't know which one was the denominator and which one was the nominator, if x0 is the root, x1 will be again be the root. If f of x0 would be in the denominator, then you have division by 0, not allowed. The other way around, x0 minus 0 divided by something, this is the correct way. So maybe you can remember by that rule, f of x0 is on top and the denominator is f prime. So this is our formula, or more general, this is our iteration. Let's have an example. Let's have this function, and we need an initial value, a starting point. Let's say we know that a root is in the vicinity of 1, so we choose 1 to be that initial starting value. Then we need for the iteration the derivative, ln x, 1 divided by x minus a third times x. Derivative is minus a third. So when we start at position 1, we need f of 1. This is logarithm of 1 here minus a third. logarithm of 1 is 0, so this is minus a third. F prime of 1 is here 1 divided by 1 minus a third, so we have 2/3. And thus we have x1 is x0, here x0, 1 minus f of x0 minus a third divided by f prime 2/3. 1/3 divided by 2/3 is 1 divided by 2, minus minus is a plus, so 1 plus a half, and this is 3 divided by 2 or 1.5. Okay, so we have one step, and then let's iterate. So we need f of 1.5. This is logarithm, natural logarithm of 1.5 minus 1.5 divided by 3. This is 0.5. Natural logarithm of 1.5 is some number, and you can ask your electronic calculator, and if you subtract a half from that, you get minus 0.0945. F prime of 1.5 is 1 divided by 1.5 minus a third. This is 3 divided by 2. 1 divided by 3 divided by 2 is 2 divided by 3, minus 1 divided by 3 is 1 divided by 3. And so x2 is our x1, here x1, the last one, 1.5 minus function value divided by derivative. Division by a third is the same as multiplication with 3, so multiplicate with 3, minus and minus is plus, and then you get 1.7836. This is the rounded version of the result. I do my calculations always with the unrounded numbers, so if you recalculate maybe the last digit, you can't reproduce. But the reason for that is I am working with the unrounded version of that number. Okay, then what do we have to do? Now f of 1.7836, and this is, and if you ask your electronic calculator, he will tell you minus 0.0159. This is an interesting information by itself, as it was here, we are looking for the root. If we test 1, the value is minus a third. If we test 1.5, the value is minus 0.0945. So this shows that 1.5 is a better estimate for the root than 1 was. And now we even get a better estimation because we are closer, much closer to 0 than we have been before. So 1.7836 is a quite reasonable approximation of the root. So this is a good information by itself. F prime, and this value is 0.2273. Now x3 is, what if that number is 0? Then we divide by 0, and that's not allowed. That means that you work with a point of that. Here the slope is 0, and then the tangent, there's no root. And that means in this case we have a very bad initial starting value, and this value is not allowed. So we tell the user, you provided an initial value which led us to a 0 slope point, and so please choose your initial value closer to the root we are looking for. Okay, so if you iterate 2 more steps, then you get 1.8572, and x5 also 1.8572. So this is a strong indication that we are close to the root because this value does not change. A second strong indication would be f of 1.8572. Most likely this value is much closer than this one, close to the 0, and so we have two indications why we are close to our 0. Okay, I want to show you electronically also one more example. Okay, let's have a look in my script. Newton's method here that we did on paper also. And here also graphics here. If this is initial starting value, then this is x1. This x1 function value, tangent root of the tangent. This is x2. x2 function value, tangent root of the tangent. And here we see after 3 steps, we are very close to the desired root. This is our formula. And what are the advantages of Newton's method? It's a simple algorithm. You will see the code is very, very short, but the user has to provide not only the function, but also the derivative. What do we have? Quadratic convergence, so that means it's much faster. Normally, it's much faster for most functions, for most cases. The convergence is much faster, so we need much less CPU time, and we find the root. If the derivative at the root is unequal to 0, if you have the following situation here, then Newton's method will not converge quadratically, but only linear. Okay, the user has to provide an initial starting value and the derivative. Disadvantages: we can find only one root. We don't find all the roots if this is the situation, and we are interested in these roots 1, 2, 3, depending on the initial starting value. Maybe we take that one, then we find that root, and maybe we take that one, then we will find that root. So once more, we can find only one root. If there's more than one root, we will find only one. We can play around with different initial starting values, but nobody can guarantee if we found 2, if there is a third one, or even a fourth and a fifth one, we will not know. So this is a big disadvantage in reality, and to be honest, our ideas following all will lack the capability of finding all roots. Unfortunately, this is a very unsatisfying situation, but this is the truth. The user has to provide starting value and the derivative as well, and the derivative is not always easy to find, as we will see in our example later in that video. Okay, this is the implementation. Input function, input the derivative of the function, input an initial value, and input a desired tolerance. Then run that loop. Here we say, okay, if 2 succeeding x0, x1, if this distance is less than tolerance, then we terminate the loop. And if this distance is more than tolerance, then we still keep iterating. Okay, then here we do the job, and in the end we return the root we have found. And here is an example how to call, but I will show you also some examples. Okay, let's come to our problem, rope around the Earth. This was in our video, the last one or the second to the last one. And here we have the radius of the Earth, 40,000 kilometers divided by 2 pi is the radius in the unit kilometers, and times 1000 means the radius in the unit meters. And this is our equation, r squared plus r times x plus a half squared minus r divided by cosine x squared. Okay, we can plot that function, and then we are looking for the root. Let's run that code till here. And we see the following horrible plot. We see a blue line and a blue line. What do we see? Not so clear. Okay, we see a blue line starting from a quarter, then going up, very steep up, and maybe this function will return and then go down deeply below 0. That's the situation. And now we have to provide the derivative. And what the f dot 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 is the derivative of that function. Okay, x is the variable and we want to derive with respect of x. Not an easy question. Our function is, and what is the derivative? We derive with respect of x, so r is a constant, then plus, now we derive a square, so we have 2 times to the power of 1 times the inner derivative, and this is r. Then we have a minus here, derivative, or ugly, is, let's reformulate, r squared divided by cosine squared. So we have an r squared times cosine to the power of minus 2. If we derive that, then we have minus 2 times cosine to the power of minus 3. We can write it that way, times the inner derivative. The derivative of cosine is minus sine. So this is the derivative of that function. But you have to be very well trained for performing that operation. And the standard user of some software will not be able to find the derivative and is 100% sure that he did everything correct. So this is a bad thing. If we want to apply Newton's method, we have to provide, or the user has to provide, the derivative, and this is often not an easy task. Here, if you are well trained, okay, it's easy, but if you are not perfectly trained, I would say this is not easy. Okay, let's go back. Okay, we saw that this is the derivative. It's 2 times r times x plus a half to the power of 1 times r, or you can write the r here if you want to, r, and take it away from here, minus r squared divided by cosine x to the power of 3 times minus 2 times minus sine x. And now we can call root Newton, and let's see what happens. Root Newton is this code, and he needs the function, the derivative, f prime, an initial value, and the tolerance. Okay, so f and f prime, initial value, let's use 0 because we assume that the solution is not so much above 0, so 0 might be a good initial value. And then we call this root Newton, and then let's see what happens. So let's run that code, and we see a funny thing. x1, this is coming from root Newton, here that line with the removed semicolon, and then he returns this x, and this means he finds minus 3.9 times 10 to the power of minus 8, and this is a nonsense answer. It is maybe a solution of our f of x is 0 equation, but it's a solution we are not interested in. We are looking for a solution in the interval x between 0 and plus 1.5. So we find a root which we are not interested in, and that's a bad thing. We used a very good initial starting value, but what we got was a nonsense answer. So maybe we need another initial value, and let's check 1. If we run it with 1, then the number of iterations performed is very high. This you will not see very often for Newton. Normally convergence is very fast, but here we see starting from 1, next value is 0.8, then 0.7, 0.5, and so. And it takes a long time, and in the end, indeed, we get the correct answer, but only because we provided a better initial starting value. But it's surprising that this is the better initial starting value, because 1 is very far away from the desired solution and 0 is very close to that, and so this is really a bad situation. Okay, if we work not with this function but with our tangent from the last or the second to the last videos, then we will have a better situation. In this situation, the function is tangent of x minus 1 divided by 2 times r. And what is the derivative of that function? What is the derivative of tangent? We have to provide that information. Okay, the derivative of tangent is 1 divided by cosine squared. But maybe you don't remember that formula. X, the derivative is minus 1, and the constant minus 1. Okay, now if we perform root Newton here, then we get, starting from 1, it takes, let's say, 15 iterations, and then we get the correct solution. If we start with the initial value 0, which is more or less more straightforward, then let's see what happens. In this case, we have a problem because here the derivative is 0. So cosine of 0 is 1, squared is 1, 1 divided by 1 is 1, 1 minus 1 is 0, so this is a not allowed initial starting value. Okay, so let's guess 0.1, and then let's run, and then okay, in this case we also find the correct solution. But you see, we need initial values, and it's not obvious which one we should take. And this is a disadvantage of Newton, unfortunately.